So there are a couple different attempts or approaches to finding the areas under curves in general. And one of them, as we've seen, involved Riemann sums, and that meant that you just cut up your interval into subintervals, create some rectangles, find the area of those rectangles as an expression involving n, and then let n go to infinity, and whatever that limit approaches, that's the actual area. Now the problem is that can be very tedious. It doesn't always work, and we just don't have time for that. It's not powerful because it's a lot of work. So another idea was to say, well, rather than get the area underneath a curve from a to b, let's just find the area under a curve from a to x. So my variable there is x, and if I can come up with an expression or formula or function that represents the area under a curve on the interval a to x, I could just plug in whatever value I want for x, and I'll have the area up to that particular x value. So that's a more powerful idea. I think it was Isaac Newton who came up with that. So that's what we're going to do here. We're going to create a function a of x, which is going to get the area under the curve f of x on the interval -1 to x. So we'll start with f of x equals 2. So there's 2. There's my function f of x. And we're getting the area underneath it on the interval -1 to x. So that area here. So a of x is going to be this area. So notice we have an expression for this area, not an actual number. The height is 2, but the width of this rectangle is just x minus -1, which is x plus 1. So the area is just 2 times x plus 1, or 2x plus 2. So that's kind of cool. If I wanted the area underneath, f of x equals 2 on the interval -1 to 200, I can just plug in 200 in for x in my area function. Now here's the most important part of this, which you don't want to overlook. If I take the derivative of a of x, what I get is 2, but that's just my function f of x. And furthermore, if we change some notation here, because we've actually seen the definite integral, we might as well use that notation since we know that it means area, net area under a curve. A of x is really just, well, it's just an integral, but the upper limit of integration is a variable. So I can write this as -1. I can write a of x as -1. Actually, I'm going to do it above. Or below. I'm going to say a of x, well, that's just an integral, right? It's a function that represents an integral. The upper limit of integration is the variable, and it's under the curve f of x. Now, I don't want to put an x in here, because if I plug in like 5 for x, I really don't want to plug the 5 in to the f part. So I need to make up a new variable just to kind of hold, just to be something to hold the place of the input for f. So that's just another, look carefully at that. That's another way of writing a of x, right? And we've used the integral notation. And so what we've just said here is that a prime of x, which is just the derivative of a of x, or the derivative of its integral name, we just said that that's equal to 2. That's just equal to f of x. So stare at that for a while. That's a very deep idea, and it's essentially the fundamental theorem of calculus, which we're going to see. We're going to look at it in a few different ways before I formalize it. So that's a very deep idea because we're connecting area under a curve with derivatives, and that is not an obvious connection by any means. Let's do this for a couple more functions. Let's do the same thing here. Let's say I got my function f of x equals x plus 1, and we want to come up with a function a of x, and I'm going to immediately write it in its integral form, -1 to x under the curve f. So let's see if we can come up with an expression or the formula for that. So there's -1, here's x. The function f of x equals x plus 1 has a y-intercept of 1 and x-intercept of -1, so it's just a line. And to get this area, I would just have to be analyzing this triangle. So the height of the function, since this is f of x equals x plus 1, when I input x, I'm going to get x plus 1. So this height must be x plus 1. And this height, again, is x minus -1, so that's x plus 1. So this ends up equaling 1/2 base times height, 1/2 x plus 1 squared. And again, we want to note that the derivative of a prime of x is equal to, now I'm just using two notations here just to, I mean, obviously I could just say a prime of x equals this, or equals the derivative of this, but I want to make the connection between this area function and this integral here, because this integral is a function. So its derivative is going to be the derivative of this guy, and by the chain rule, that's just 1/2 x plus 1 to the 1, which is just, oh, sorry, it's 1/2, it's 2 times 1/2, it's 2 times 1/2, right? Bring the exponent down. 2 times 1/2 x plus 1, which is just x plus 1. But that's just f of x. So again, we've said that the derivative of this thing is just f of x. The derivative of the integral function, which is getting you area under a particular function on the interval -1 to a variable, is just the function itself. Let's do one more. So we'll finish with one more example. F of x equals 2x plus 3. So we're trying to find an area accumulating function, a of x trying to find an expression for that function. 2x plus 3 has a y-intercept of 3 and a slope of 2. So when I plug in -1, I get out a 1. So it's going to look like this. So there's my function f of x. We're interested in this area here. Again, this expression, this base here has length x plus 1. The height has height 2x plus 3. And this is a trapezoid. This height here would be 1, so I'll call this a 1. Okay, so that's a trapezoid. We can get the area of that trapezoid. The area is going to be the sum of the bases, so 1 plus 2x plus 3 averaged times the height, which is x plus 1. So that equals 2x plus 4 over 2 times x plus 1, which is x plus 2 times x plus 1, which we can write as x squared plus 3x plus 1. And as if you didn't see it coming, I'm going to make the final note here, which is that if I took the derivative, a prime of the derivative of my area accumulating function, that's the same as taking the derivative of how I write it in integral form. And its derivative is 2x plus 3. Right, its derivative is 2x plus 3, but that's just f of x again. So in our little journey here for coming up with these area functions, we've noted that the derivative of these area functions is the function under whose curve we're actually finding area. And that is the fundamental theorem of calculus. That's one part of the fundamental theorem of calculus. So I'll prove that in the next video, and we'll look at some examples. It's a big part of understanding this is that we can now write functions in integral form, where if we let this upper limit of integration be a variable, I've come up with a whole new family of functions that can be represented as integrals. So you'll want to start like adapting your mind to that idea, so that you can be fluent with seeing them in different contexts and comfortable with them. And it'll take some time, but you'll get it.